Welcome back, everybody. We're in the middle of renegotiating the homework dates. So this was homework 2. This was originally due October 4th, which is next Wednesday, which does feel a little bit ambitious. And I'm not in the mood to say, I'm going to show you everything you need to know today, so get to it. So I think we can extend a little bit. So we've been a little bit ambitious about our schedule. I think that's okay too. So we're renegotiating the homework date. So is this good? You guys like this? Does ever buy a car or anything like that?
See, in my mind, right, I was thinking, like, what's a good happy medium? Of course, fire would be awesome, right? But, like...
You never bought your own car with your own money.
But, like, for happy medium for both you and us, I think Wednesday would be great.
I always try to craft, like, a good reason to get what I want. You know, and see if I can convince that person, and then they walk you back a little bit, and they tell you what they want, and then you compromise. Maybe that's what you've done. So you kind of like thought what I would already agree to,
yeah,
and what you could live with.
Yeah.
Or negotiate.
Yeah. Well, I didn't want to try this out.
Nice guy tried to do all the negotiation all in one fell swoop. Note that October the 6th is a day off for us. So October 6th, this is Friday. This is fall break. They give you one day off. So in all of this, so you're thinking, knock this thing out. So next Thursday we do a review session, then you guys go on break, then you turn it in, something like that. And you're kind of thinking that because we've got this original deadline. So homework 3, what's due on this? This is a Friday as well. But since we were taking that day off, we would push to the Monday. We also have on our schedule a midterm that's due, that's on October the 30th. This is a Monday as well. So Monday. So I'm looking at all of this and I see a slightly different story. Anybody want to renegotiate? No.
Monday, October 9th.
What's that? Oh, you want to renegotiate to make this due on Monday, October 9th?
October the 11th.
I can't wait to sell you a car.
Right after fall.
What's that?
Said I wouldn't want to do on that Monday, so that if people do want to do something for fall break.
That's what I'm thinking too.
Don't want to do it Monday.
So I'm not saying that this, you know, the fall break isn't enough, but Thursday night we would do the only review session, pushing into that. So I'd kind of like to be a little bit more generous about this and give you 2 options for a review session. I know if it was me, I'd be out of here on that Thursday. I'd already be gone. So anybody have plans for this weekend? I do too. So, but I'm going to be here for that Thursday. I think we can do a review next Thursday, and we can do a review the Thursday after. We can probably turn it in on the Friday. So I think that might make a little bit more sense. And so probably this anchoring that you were thinking about probably could be pushed to here. So we can probably turn that in on the final and get another review session in there. So, and everything due at once, you walk in with your homework due, it'll give you a chance to kind of study. Hopefully you're doing studying and working on problems early though. So, how about this? If everybody says they don't wait until the very last minute on homework to do it all, and they're being proactive, which I think you are, then we can build in review session next Thursday, the Thursday after, and turn in the homework the next day. Everybody promise? You guys know what a promise is? Raise your hand if you promise to keep studying and working your problems early so that you have good questions in review session. Hands up if you promise. One, no promise, and we don't do it. Hands up high if you really promise. Hands up high if you promise. No fingers crossed. Okay, I believe. No? Oh, the pressure. Okay, let's keep working the problems and trying to get through them. A lot of stuff is already done. I was kind of looking at homework 3, and we're going to do a lot of it today. So, you know, a lot of stuff is built in, but really I want everybody to do well here. So that's the important target. So make sure you're practicing the problems, because if you cram at the end, it won't work. So I say, let's make this due on the 13th. Is this right? And this is a Friday? Yes. That's easy to remember.
What Friday is the 13th? In October. It's like bad juju right there.
So when can we look at the results of our homework to see where we went wrong?
Yeah, that's a good point. So I do have homework 0 for you. I just keep forgetting to bring it back, but they're all like 99s or 98s. So I can tell you that already. So there wasn't anything too crazy. Yui has the homeworks right now. He'll probably be done grading them. I'm going to guess this weekend, and I'll probably have them for you on Monday or Wednesday. And then we'll be able to iterate for Thursday, the review session. Is that a good schedule? Good. Okay, cool. So you will be getting it all back. Sorry, I keep forgetting homework 0. It's just not something that's burning a hole in my mind because it's not that important. So who said Bayes first? Fisher. So 3 great answers to who coined Bayesian. You know, who's like founder of Bayesian statistics? You know, those are kind of different questions. Who coined the term? So Fisher maybe said it first, but I think Dave Finetti wrote it first. Jack Good picked up on it and passed it off to Savage. So the founder of Bayesian statistics, I don't know. So Laplace, I kind of like that, is an answer. But obviously there's a huge contribution of everybody coming in together. Some people will say things like Lindley, and sure, he gets a lot of credit for kind of like making a massive push, but he's hardly a founder. So if you said anything like that, you got full credit. And if you said anything close to that, but a little bit weird, you got -1 on that problem. So something like that. Those are the answers, at least to homework 0. Okay, I think we've got a good schedule here. So I think I'm going to do homework 3 is, I'm going to leave this right here, but I'm thinking of maybe a push if we need to, or something like that. So I probably wouldn't want it to be due exactly right here, so somewhere in the middle of this, but I'm going to leave this on the board. Okay, so we've got some updates on everything. I'll copy this over to the Slack page and just write it on the Slack page so that we have a permanent record of it. Cool. Okay, so today, we're in the middle of this calculation. So we want to figure out a forecasted data point. So that's our forecast. Predicted value. So this is something future, it hasn't happened yet. And so we get to observe a bunch of x's, where these x's were IID and they're coming from a normal distribution. We're going to say we know this sigma. Probably looked at the first problem on the homework set that's due soonish, but not too soon. It's all about the problem without sigma squared in there. And no surprise, it's going to change everything that we do into t distributions. And I give you kind of a weird way to work through it. So I have you work out the posterior distribution of phi given x, where you marginalize out mu in advance. So I'll just give you a heads up, that's a gamma distribution. The goal is to figure out which one it is. So it's different than if you condition on mu. So we're going to say this is known. So we get to use that in here. And so what we're really doing is we're going to marginalize out this. So we're going to just write down that any one of the fx's I, given mu and sigma squared, we know what its sampling density is. It's just this. Sigma outside of the square root, e to the minus 1/2 xi minus mu squared over sigma squared. So this is the sampling density. And if we knew mu and sigma squared, we could use that to predict the future. So it tells us future observations are like that. They're centered around mu and it's got variance sigma squared. And so you can never get away from this variance in making a forecast. And so that's why probably some of you are saying if we forecast into the future, probably the variance is sigma squared. But that's assuming we know mu. We know we're going to estimate in some sense mu with x bar under the flat prior. So that's what we got before. And there's uncertainty to that estimate. And that uncertainty is sigma squared divided by n. What's the total variability of the prediction? We're inclined to add those things together. If you're not inclined to do that, you'll be inclined after we solve the integral. So we don't know this. We need to marginalize. As Bayesians, that's what we do. So we want to forecast this thing. We made some guesses about this. We guessed with a little bit of help. So that the variance of x tilde, given all of our previous data and knowledge of sigma squared, was sigma squared plus sigma squared over n. Some of us guessed this, or at least I'm going to pretend we guessed this. So those are my little quotation marks. So not all of us were completely convinced. So we could just write this down like this. And there's some reason behind it. This is the total variability of a future data point. If we knew mu and sigma squared, we at least know that the variance needs to be greater. And the only uncertainty in the problem is this thing right now. So we also guessed this is true. So Josiah guessed this, and he seemed pretty confident at the time. It's x bar, but absolutely. So, and we will derive this. These are all true. And we also surmised, by glancing at the definition of this and looking at the integral and seeing what we might factorize out, we guessed that this thing right here is maybe normal. So we have an answer on the board, but now we're going to construct that answer from scratch. I'm going to give you a 2-for-1 in this lecture and tell you if I didn't know how to do the integral, what I would do. So, but just real quickly, the integral we need to solve, I get upstairs, give myself maximal room. Actually, I'll put it over here. Max room. This is going to be equal to f x tilde. This is the random argument. So this is going to be given mu and sigma squared. If you'd like to condition on the data, it makes you feel better, that's okay. But if you actually knew all the parameters underlining the distribution, None of the previous data helps you with anything. And we're going to weight over this sampling distribution with some weights. Into a Bayesian, they would use the posterior as their weights. Kind of makes sense. It's telling us what we think mu is, putting a distribution on them. So we already know this is normal x bar sigma squared over n. So this assumed we use the flat prior. And we know this thing just from the sampling process. So it's just that. So this is just a normal mean mu variance sigma squared. So just so you know, if you take a normal times a normal and you integrate over it, it's a normal. Never forget that, it's true. We'll prove that in a second. We'll do a calculation and demonstrate it. So, but it's normal, and probably no great surprise. Okay, so just in general, let's just say I've got our data is coming from some process f of x given theta. So just back to our general notation, whatever these parameters are, you know, they're the parameters that underline the distribution. So for the normal example, the theta represents that. In an exponential distribution, it's the rate parameter or scale, depending on how you deal with it. In the gamma, it's alpha and beta. So it's that stuff, the parameters underlying the distribution. So I'll just make this like this, although this doesn't actually have to be true. So, and I'm going to say we've got some posterior distribution. Our posterior on theta, given all of our data. So in our data, it's going to be all of the xi's. That comes from whatever this process is. So we have the posterior. The posterior predictive distribution is just this. Fx tilde, that's just an argument for this density function. There's actually nothing specific saying this needs to be a density. That could be a probability distribution. So I haven't said what the support is for x tilde. If it were discrete, it doesn't necessarily mean that theta is discrete as well. So theta could be continuous. The binomial is a good example of this. So if we did this and x tilde was on a probability scale and this was a mass function, this wouldn't be a density and this would be a mass function. So we'll see examples on that as well. So that's just true. So for Bayesian, if you've got the posterior distribution, if you're able to find it in closed form and know and recognize this distribution, know all of its properties, and you can sample from that distribution, this is a relatively straightforward calculation. So you might not get an exact thing, but we can come up with a Monte Carlo estimate of this right here. So let's just outline a Monte Carlo scheme. I don't care what this distribution represents. I don't care what that represents. I don't care what that represents. These are all just true statements. So I went through probability class and that's just true. So this is just marginalization. So you don't have to apply this Monte Carlo scheme to necessarily just posterior predictive samples, but you could apply it to anything where you're mixing theta over some other distribution. So in some sense, this is a mixture distribution. So I'm mixing this distribution with that one. I'm marginalizing over theta. So combining them in some way. So what do I mean when I say I combine those two distributions and I average over theta? I'm mixing over them. So I don't think that's too difficult of a concept. So we will re-encounter this word mixture later on, but this is just some mixture distribution right here. So all I'm really doing is I'm just weighting this sampling with that. So it's just a weighted average. So when I see that equation, I just see weighted average. So if these things add up to 1, then it's just a typical arithmetic weighted average on a continuous scale. So the Monte Carlo sampling we could do is I could sample theta. I'm going to call it theta, I'll just put an index on it, I, and I can take this from its posterior distribution. So I can sample all of my weights right here. I'm just going to sample one at a time. And then I can take that weight and I can bounce it into this distribution. So I can take f of x tilde given theta, and I can drop this theta right in there. And I'll call this theta I. And what I'm going to output from there is x tilde, and I'll index it with the same index as well. So all I've done in getting everything right here is I've really just collected a joint sample. So a joint sample from this joint distribution. So the joint right here, I'll just call it f of x tilde theta given x. And just so that the pi's in there, I'll just throw the pi up there. So it's some joint distribution. I don't know what to call it. So just like the normal gamma, it's the product of these two things, and they had some connection to each other. So this is a joint, and this is a joint sample from it. So, and we can break it up because this joint distribution has been factorized into a component that just involves theta, and once I know theta, I can get the x tilde. So this is Monte Carlo sampling. And if you understand this, you understand what that integral means. So let me just ask a question. How are we weighting everything? We're weighting everything by this distribution. So this has some shape right here. So this area is bigger than this area. How am I making sure that I'm weighting things more heavily in this region than this region through this sampling scheme? We can probably see it in the integral. When I integrate over this, it's integrating over something that's higher in the integrand. So it's elevating everything. Everything's positive in there, so it's making it bigger. So, are the weights implicit here? How many samples do I get in this region? I'll say this is A2 relative to this region. I'll call that A1.
Or I guess it would be the ratio of the areas.
Yeah, it's the ratio of the areas. So you get how many samples relative to this? It would be the ratio of the areas. So how often am I sampling in this? It's proportional to its area. How often am I sampling in this area? It's proportional to that. So just by sampling out of this, it's going to sample more times from this area and upweight those samples when I sample these x tilde. So when I see an integral, I think a process. Every single time. This is some process, and I'm just averaging over things. And so hopefully you can see that as well. But this is just your typical Monte Carlo sampling scheme. So for the normal example, this is really easy to do. So for this problem that we're solving, this one, we could collect samples. I can't write down the distribution analytically. I might not know that this thing is normal, but maybe I don't need to. So for our example, do sigma squared where sigma squared is known, what I would do is I would end up getting a mu I. I'd get it from its posterior distribution. So I know what this thing is. It's a normal centered at x bar with variance sigma squared over n. Do you know how to sample from this distribution? If I said, please give me 1,000 samples from a normal, what would you do?
Don't you have to look at the inverse of the CDF?
I hope not, because that's impossible in that example. You'll never write down the CDF in closed form. It's the earth function. We'll always bark back at you in MATLAB or R or Mathematica. So no, you can't write down the CDF in closed form.
For that number, and I know you can approximate.
Okay, so you're going to approximate. Then I can approximate using the inverse CDF function too and build stepwise approximation to the CDF function. I can invert that. So I can build an approximator to it. I'm just saying if somebody came in right now and said, I will give you $1,000 for every normal sample you could give me in the next 10 minutes, how many could you give them? So you would tell them that, I'll just give you 2 uniforms and you'll be broke.
So he did use it before to get it normal.
You could, that's true. I could do that. Do you know how to do that? Okay. Would anybody, so let me just ask a question again. This isn't a trick question. Somebody walks in, this is a hypothetical, nobody's gonna do it, and says, I will give you $1,000 for every normal sample you can give me. How many could you give them in 10 minutes? So you're saying you would go to the library and figure out what this method is. Go to Wikipedia, hopefully you can code it up real quick.
We could just use R and use.
You just go to R. So bam, put in a big number, 1 comma, they'll give you normal 0 1s if you don't put in the mean and the variance, and you could shift them and scale them yourself. So you could take your normal 0 1, shift scale them to any distribution they wanted. So real quickly. So you'd be wealthy, right? Just go to R, you push the button. So is that how you do it? So there is an algorithm called Box-Mealer that for 2 uniforms, it will give you 2 normals. I'm not going to teach you how to do that, but that's how your computer does it. It doesn't do an approximation to the inverse CDF. You could do that. So you can't write down the CDF in closed form, but I can come up with a numerical sort of approximation to it. I could use a binomial approximation and do even worse. So, but you might say, what's n, what's p, all that. So you're right. That's actually where the normal curve came from, is binomial approximation to it. So that was the original incarnation. I learned that recently. So yes, you could do this. You go to a computer and you say, what's the command? rnorm. Yeah. And there's also random, quote, normal. There's a lot of ways to input that thing. So rnorm. Does anybody know what it is in MATLAB?
Random.
What is it?
Isn't it just random?
I thought that was right.
RM.
rand. Rand n. So rand is a uniform, right? So and then rand n. You can check them out. So, but yeah, you could just punch it into your computer. We know how to do that, or at least somebody knows how to do that. So if we ask ourselves enough, do we really know how it works? We wouldn't even be able to use our microwave. So we're allowed to take this for granted right now. So then I'm going to take this sample and I'm going to plug it into the sampling distribution. So I'll have x tilde sampled with this mu I. I still get to know what sigma squared is right here, so that's known. And I'm just going to take this thing, x tilde I, and I'm going to take it from that. And this is just a normal centered at mu I with variance sigma squared. And we could do the same thing, use our norm, and just sample out of it. So we could do this a bunch of times. I goes to 1 to whatever number makes me wealthy enough. So if I ask you for predictive samples, we can make this big. And at the end of the day, what you actually get is you get joint samples. X tilde I and BY. So these are posterior samples. And these are predictive samples. Those are your predictions. And you'll get a whole collection of them. I goes from 1 to whatever that number is. And they're all perfect samples for that distribution. So I just sampled twice from a normal distribution. You'll see this when we do the integral. This is why we have 2 integrations that we need to do. So if I got rid of these and just chopped them out, I have marginal samples from this distribution. So just by throwing away a column of samples is integrating. So you've averaged over them. The x tildes were intertwined with the thetas along the way. They've already been accounted for. You can just toss them. So that's Monte Carlo integration. Bam, done. So that's kind of cool. So that's something that I ask you to implement with the t distribution to sample from a t in disguise in the homework. It's not applied to a posterior predictive, but it's a mixture. It's a scale mixture over a gamma. So same exact sort of process. Let's say we want to know more. Let's say I'm not satisfied with this. All you can give me at the end of the day is a histogram of these samples, and I want to be able to verify that they're normal. I want to be able to do some like thinking about this distribution. Instead of just being an engineer and give me the samples, I'm going to do something with them at the end of the day. I'm going to just use them for prediction. You sample a bunch of times, I can give you intervals from this. So if you crank that number up, I can give you the mean of that distribution by giving you a Monte Carlo estimate of it. So let me just ask this question. Say we want an estimate of x, the variance of x tilde given x, and you want to know this sigma squared. And you get to know this sigma squared at the end of the day. So I want an estimate of this thing. But all I get is these samples. So I have cap K samples, and let's say this is a bazillion. So it's some tremendously large number. How would you estimate this? Not all at once. I can't hear you over the deafening noise.
S squared
S squared. S squared with what?
with your samples.
Yeah, probably something like this. X tilde I minus X tilde, this is horrible notation, bar. I'll fill in what that means in a second. Square those things out, divided by K minus 1. I goes from 1 to cap K. So what is this thing right here? That's just the sum of the X tilde I's divided by cap K. It's from 1 to cap K. So this is just the average. So this is an estimator of the mean of the distribution, and this is an estimator of the variance of the distribution. And I would never even quibble about that or this, because I get to control K. So I love asymptotics, as long as I get to control what the sample is. And in Monte Carlo land, you get to control it. So it turns out I'm also a frequentist. So when I get to control the frequencies. So we'll get to that later when we study Monte Carlo. So I use frequentist principles to debug my Bayesian Monte Carlo scheme so I can get Bayesian answers. I use everything. This is a perfectly frequentist answer using these Monte Carlo samples from a Bayesian posterior. Okay, so that's a Monte Carlo estimate. Let's do the integral. This thing, if K is very large, this will converge to sigma squared plus sigma squared over n. So I'll just make that point. So this thing will converge as cap k goes to infinity. So to sigma squared plus sigma squared divided by n. So it's kind of nice if you actually have the real answer. Let's say you're going to use this answer somewhere and you have to recompute it all the time. Having an analytical answer will speed everything up. So let's do the integral. So this is going to look like this. Normal times the normal. I'm just going to do my first step and get rid of my normalizing constants and make sure I don't throw away anything that has to do with the random variable or anything that I'm integrating over. So the mu in all of this. So this is going to look like e to the minus 1/2 x tilde minus mu squared over sigma squared times e to the minus 1/2 mu minus x bar squared over sigma squared divided by n. We're integrating over mu, which appears in both parts, which makes sense. We're integrating between negative infinity to infinity. I'll probably stop writing that down. So this is a definite integral. So what I want to do is I want to recognize that this integral is going to be e to the minus some quadratic form. I'm going to be looking for its square term in x tilde, and I'm going to be looking for its -2 linear term to identify the mean. So square term will help me with the variance, -2 linear term with the variance in hand will help me untangle the mean. But I got to work through this integral first. So I can get it into some form I can recognize. So let's begin. So integral e to the minus 1/2. I'm just going to start expanding everything. X tilde minus, this is x tilde squared minus 2 mu x tilde plus mu squared. These are all divided by sigma squareds. You'll notice that I already I'm thinking about mu first because I've got to integrate over it. So I threw mu over to the left-hand side. So that was just a choice I made because it's going to help me to recognize everything. And remember which step I'm on. E to the minus 1/2. This is mu squared minus 2 mu x bar plus x bar squared. So this is divided by sigma squared over n. This is sigma squared over n. This one's sigma squared over n. D mu. If I can remember to write those, I'll keep doing it. Is there anything we can factorize out of the equation? And just start throwing away. We've already taken the first step and wrote this thing down up to proportionality. If you did collect all your normalizing constants throughout everything, they would turn out right. And so if you want to do that, go ahead. So I never do. Anything we can throw away out of the equation? Can we throw this away? No. So we can factorize it outside of the integral. So let's just do that real quickly. So I'm just going to write this down, e to the minus 1/2 x tilde squared over sigma squared, integral. So I just plucked that out, factorizing it out of everything. You could end up making this a little bit nicer looking just by doing this. Combining everything into one exponent. But everything factorizes out just the same. So don't lose this. Hold on to it because the distribution is all about x tilde. So, but we can at least get rid of it from our integral. Can I get rid of that? No, there's a mu. No, no, no. How about that one? I can factorize that out, same thing, and chuck it. It's got no mu's in there, no x tildes. I'm just going to get rid of it. So let's rewrite this. E to the minus 1/2 This is going to be, I'm going to put my mu squareds up front. I like to do that just because I don't like these minus signs leading my equations. So I'll just put the mu squareds in here and I'll combine both of them that appear. So there's one there, 1 over sigma squared, and there's one there. 1 over sigma squared divided by n. I'm sure I could write that a little bit nicer. So minus 2 linear. And I've got 2 of those terms as well. So I've got this one. Yes, x tilde divided by sigma squared. And then I've got this one. Plus x bar over sigma squared over n. d mu. So possibly I can recognize what this is. Anybody have any idea what this integral is? Let me just write down a few things real quickly. This is a normal. So it looks like the kernel of a normal. So that's what I normally mean when I say it's the kernel of the distribution. It's got all this elements that I need for it to figure out which normal it is, but it's got a variance. And I'm going to give it some importance. So I'll put a star on there and make sure we can remember what it is. It's right here, inverted.
So should we end up with something like square root of 2 pi times whatever that variance is that we end up getting?
Something like that. Anybody else, since we're going to carve in a gex?
This result should be 1 over the coefficient in mu squared and times.
Let's give us some more notation, just real quick. Let's come back to this. We haven't finished writing. No disagreement, that belongs here. So this is going to be 1 over sigma squared plus 1 over sigma squared. I'm going to make it nicer. So n over sigma squared, inverted. So what does that look like? This is n plus 1 over sigma squared inverse is equal to sigma squared over n plus 1. Feeling good about things right here. Seems to smack at the answer. So expectation, let me write that up here. How do we find it? Grab this thing, multiply it by your answer here. So this is going to look like x tilde over sigma squared plus x bar over sigma squared over n times sigma squared over n plus 1. So we've got a little bit of cancellation in all of this as well. So, just kind of cool. You think this answer has anything to do with E?
Since it's proportional.
E has some answer in here. The V actually is the thing that doesn't matter, because it has only fixed stuff in here and up to proportionality, but we're writing equal. Does anybody know what this is?
This is our normal mean and the expectation and variance of eta. Right? So as it's -1/2. And then we'll have, after do the cancellation, mean that x tilde plus an x bar over n plus 1.
Forget about the cancellation, let's just use this stuff. I've got symbols.
So we know our random variable is now x tilde.
Forget about it. We've got E and V.
X tilde minus e.
Forget about it. Just E and D. All you need is to talk about those. that has your x tilde in there. Okay, let's see. So let's come back to this. This is not right, so let's check here, and there's some answer here. So I'll just tell you what it is. So let's just see it. So this is just completion of the square. We're trying to do that all in our head real quickly and figure everything out. Let's just expand the square. So just aside, let's remember stuff about our normal distribution. So let's say I have a normal. It looks like this, e to the minus. So if I have fz mu sigma squared, so that's just what a normal looks like. The kernel, everything I need to know. If I wrote this out like this, e to the minus 1/2, I've got a z squared term times 1 over sigma squared. I've got a minus 2 linear term times mu squared over sigma squared. And I've got a mean squared over a b squared, sigma squared term. We're missing this. We have all of these. So we're missing this term, which is the expectation squared divided by the variance. So if I can recognize in here what the expectation and the variance are, I can just take those things. This is the expectation squared term divided by the variance, but I gotta flip it upside down. This has a, what sign on it? Plus, minus, invert, plus. You can do that. So this is plus right here. And I always mess that up. So I like to do this to remind myself that's a plus right there. So just convince yourself this is that term being flipped upside down. This is the other stuff in the normalizing constant, so this is exactly right. So this is equal. Let's carry on, just jump into the next step of everything, and we'll finish up this thing next time in a couple minutes. So what we have so far, this is what we've worked out. Pi x tilde given all of our data, we get to know sigma squared. This is going to be proportional to, don't forget that, this is e to the minus 1/2 x tilde squared over sigma squared times square root 2 pi. We probably could get rid of that 2 pi if we wanted to right away. B star. We can shut that as well. If we didn't know what the variance was, we'd be making a horrible mistake by throwing that away. So this would be part of our answer. So, but since we know what sigma squared is, and this thing only has sigma squareds in here, it's a constant to us. So times e to the plus 1/2 e star squared over b star. I want you to remember this. When you integrate over two normals, if you can recognize what the expectation and the variance is in the integrand, your answer is that. And if you don't want to remember this part, that's okay. So you can get rid of that. So this part for us right now, we can get rid of this whole thing. So this is going to look like this. E to the minus 1/2 x tilde squared over sigma squared. It'd be enough for me just to glance at that and to say this thing is going to be a normal. It's not going to be anything else. So maybe that's just because I already know this is quadratic in that same term. So e to the plus 1/2. And let's just write this stuff in here. So this is going to look like x tilde. We can leave it in simplified form just to see everything up here. So x bar over sigma squared. Let's leave it in like expanded form. Already got that. So times sigma squared over n plus 1. We need to square this. This is the e squared part, divided by our variance, which is just sigma squared over n plus 1. This is all squared. We probably need to do a little bit of simplification here. So we have an opportunity to do that, but just to recognize, this is e to the minus x tilde in some quadratic form. When I expand that, which we'll do next time, we'll be able to collect all the quadratic terms, the minus 2 linear terms, and if we haven't made any mistakes, and I feel pretty good about this so far, we'll be able to recognize the mean of this and the variance. So why don't you just try over the weekend to get that mean and variance, and we'll come back and verify it after you verify it to yourself. The mean is x bar, the variance is going to be sigma squared times 1 plus 1 over n. Okay, that's enough for now. After we finish this integral, which should only take us a couple more minutes of just expanding and recognizing the same trick that we've done a bunch of times so far, I'll show you the fast way to do this problem. Great, you guys. Have a great weekend.